Download this code from codegive.com, link in the description below. OK, let's dive into a comprehensive tutorial on collections in Milvus, focusing on their role in retrieval-augmented generation, RAG, for generative AI. We'll cover everything from basic collection creation to advanced indexing strategies, and illustrate with code examples. Understanding collections in Milvus, the foundation for RAG. Milvus is a vector database. It stores high-dimensional vectors, which are numerical representations of data. These vectors are crucial for tasks like semantic search, recommendation systems, and, in our case, RAG. A collection in Milvus is analogous to a table in a relational database. It's the container for all the vectors you want to search and retrieve. For RAG, we'll typically use collections to store vector embeddings of our knowledge base, documents, text snippets, etc. When a user asks a question, we'll 1. Embed the query * convert the question into a vector. 2. Search the collection * find the vectors in the collection that are most similar to the query vector. 3. Retrieve the context * get the corresponding text snippets associated with the similar vectors. 4. Augment the generation * feed the question and the relevant context to a large language model, LLM. 5. Generate the answer * the LLM uses the context to provide a more accurate and informed answer. Prerequisites. Milvus installation * make sure you have Milvus installed and running. The simplest option is to use Milvus standalone with Docker. Follow the instructions on the official Milvus website, https://milvus.io/docs/install_milvus.md, https://milvus.io/docs/install_milvus.md. Python environment * you'll need Python 3.8 plus and the PyMilvus client library. Sentence transformers, for embeddings we'll use sentence transformers to create vector embeddings. LLM setup * you'll need an LLM API key, example OpenAI, Cohere, Hugging Face Inference API. This example focuses on the Milvus part of RAG, so I'll provide a placeholder for the LLM interaction. Step-by-step tutorial, building a RAG system with Milvus collections. 1. Connect to Milvus. 2. Define the collection schema. The schema defines the structure of your collection. We'll need fields to store. *ID, a primary key to uniquely identify each entry. Embedding, the vector embedding of the text. Text, the original text snippet. Source, optional, a field to store the source document or origin of the text. 3. Create the collection. 4. Prepare data and embeddings. Let's create some sample data and generate embeddings using sentence transformers. 5. Insert data into the collection. 6. Create an index. Indexing is crucial for fast similarity search. Milvus offers various indexing algorithms. Here, we'll use IVF_flat, a common and efficient choice for many scenarios. Other options include HNSW, ANOI, and PQ. Choose the best index based on your data and performance requirements. Explanation of index parameters * metric _type, specifies the distance metric used to measure similarity. Metric type. Cosine is a good choice for text embeddings, as it measures the cosine of the angle between the vectors. Other options include L2, Euclidean distance, and IP, inner product. Index_type, the algorithm used for indexing. IVF_flat, divides the vector space into clusters. During search, it only compares vectors within a subset of clusters. It's a good balance of speed and accuracy. ANList controls the number of clusters. *HNSW, hierarchical navigable small world. Creates a graph structure for efficient neighbor search. Generally faster and more accurate than IVF_flat but uses more memory. *genai, another graph-based indexing algorithm. *PQ, product quantization. Compresses vectors to reduce memory usage, but can slightly reduce accuracy. *params, index-specific parameters. For IVF_flat, ANList is important. Larger ANList values generally lead to better search accuracy, but slower indexing and more memory usage. Start with a value like 4*sqrt, n, where n is the number of vectors in your collection, and tune from there. 7. Perform similarity search, query the collection. Explanation of search parameters *** metric_type, must match the metric type used when creating the index. *params, search-specific parameters. For IVF_flat, nprobe controls how many clusters are searched. Larger nprobe values lead to better accuracy but slower search times. Start with a value like sqrt, ANList, and tune. *limit, the maximum number of results to return. *expare, allows you to filter the search based on a condition. For example, you could restrict the search to documents from a specific source. *output_fields, specifies which fields you want to retrieve in the search results. 8. Integrate with an LLM, placeholder. Now, we'd take the retrieved context from the search results and feed it to an LLM along with the original question. Here's a placeholder for that step. 9. Cleanup, optional. Complete code example, concatenated. Important considerations and best practices. *data chunking * for large documents, break them into smaller chunks, example sentences, paragraphs, before generating embeddings. This improves retrieval accuracy. Experiment with different chunking strategies. *metadata filtering * use the expare parameter in collection.search, to filter your search results based on metadata, example source, date, topic. This can significantly improve the relevance of the retrieved context. *index selection * carefully choose the right indexing algorithm based on your data size, query patterns, and performance requirements. Experiment with different indexes to find the optimal configuration. *quantization * for very large data sets, consider using quantization techniques to reduce memory usage. *monitoring and tuning * monitor the performance of your RAG system and tune the indexing parameters, example ANList, nprobe, to optimize retrieval accuracy and speed. *error handling * implement robust error handling to gracefully handle exceptions and prevent your application from crashing. *scalability * for production deployments, consider using Milvus cluster for scalability and high availability. *hybrid search * explore hybrid search techniques that combine vector search with keyword search for improved relevance. Milvus supports integrations with other search engines. *relevance scoring * implement a relevance scoring mechanism to rank the retrieved context snippets based on their relevance to the query. This can help the LLM focus on the most important information. *context window management * LLMs have a limited context window. Carefully manage the amount of context you provide to the LLM to avoid exceeding the limit. Consider using techniques like context compression or summarization. This tutorial provides a solid foundation for building a RAG system with Milvus collections. Remember to adapt the code and techniques to your specific needs and dataset. Good luck.